Welcome to Thermal Engineering Concept and Principle. This is Professor Ali Tarra. What do you know about vertical heat exchangers and their philosophy of operation with geothermal heat pumps? We mean here the operation of the borehole geothermal heat exchanger. To know that, come with me to go through details of the present episode. Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present episode is related to the geothermal heat pump components and a full description for these components and their layout with the geothermal heat exchanger, and then we will go to the direct contact geothermal heat pump, which includes the heat exchanger, which is called the DX geothermal heat exchanger, where the same fluid that is circulated through the heat pump is also circulated through and passed through the geothermal heat exchanger, which in this episode we will go to the double U-tube vertical heat exchanger, because all the previous episodes were describing the single U-tube heat exchanger, and this is how can we deal with the double U-tube heat exchanger. And finally, we will arrive to the closure as usual for each episode. The main structure of the W tube heat exchanger is composed of borehole and double U tubes where they are installed inside this well, and they are surrounded by a grout material which should be in a good thermal conductivity to pass heat uh, uh, through this material between the fluid inside the tube and the surrounding grout and the soil material. This illustration shows a single tube, but it is in fact for a double U-tube. When you look at it from the top, that we have two U-tubes, one side for the inlet and the other for the exit part, and these tubes are installed in parallel in the well, and at the same time they receive fluid in a form of parallel arrangement, and then the exit is collected in one header and leaves the heat exchanger. This is the type of where we are going to analyze and model during the present episode. Here we have the condenser, which represents the fourth main part of the heat pump itself. So we have the underground heat exchanger, the borehole, represents the condenser, and the other parts which compose of evaporator, compressor, and expansion valve represented by the other side which is out of the ground. Then what we have, the ground part represents a condenser. Here we have the refrigerant vapor which is circulated in the heat pump, passes through the inlet part of the heat exchanger through the red line, and then it reject energy to the ground, of course, through the filling or the grout to the ground, and then returns as a liquid refrigerant to complete the closed circuit of the heat pump. Again, this is a DX geothermal condenser because we didn't need an intermediate fluid to transfer energy to the ground, because the main principal part which represents the fluid that is circulated in the heat pump is the liquid which passes through the heat exchanger. To analyze the borehole with a double U-tubes, let us consider that we have this arrangement of a double U-tube heat exchanger with design specifications S sub P, D node, and D sub B for the borehole, and it is surrounded by the soil. So how can we deal with the double U-tube and to model it and analyze it to get a final form of equation where we can use to predict its depth? Let us go back to the same assumptions which we have used previously, where we can consider the grout material volume is the same for both the original design and the equivalent design. And let us assume that we have W tube they are identical and similar in their dimensions, such as the length and the diameter. So we can consider the inlet part, which is shown in the green uh, color, or even the exit part, which is shown in the blue part. If we consider the inlet part, then the volume of the groove should be constant and fixed for both geometries, which leads to d equivalent equal to square root of 2 times d naught, which is the same form which we have obtained throughout our discussions for the design of a single YouTube. Now, let us transform this geometry to equivalent one as shown in this figure. Then we have the inlet part, which is represented by the green, and the exit part, which is represented by the blue. And generally, for previous episodes where we have used uh, uh, the similarity and analogy between the thermal resistances and the electrical circuit resistances as shown in this figure, and we have derived the borehole thermal resistance, and you may find a full description of the present analysis in this reference, where could be found in the list at the bottom of this video in the description box, which is represented as the first reference in the list. And we have here 5 thermal resistances. For 2 of them are for the pipe, which are identical and similar and equal. And then we have the thermal resistance between the surface of the tube and the grout material. We have 2 legs here. Then we have 2 resistances. And one is the resistance of the shank between the tubes. If we summarize our analysis for this geometry, we have the spacing or the shank in effect between the tubes, which is should be equal for both geometries as it is imposed in the present model. S sub p minus d naught equal to S sub pe minus the equivalent, which is represented by equation number 2. Then, if we use the description of each part, then we can reduce this equation to L sub Pe equal L sub P plus 0.207 times D naught, which is represented by equation 3. And then we have the shape factor for eccentric tube in a cylinder, as shown previously in previous models as well. And then we have the thermal resistance of the offset tube or cylinder inside another cylinder, which are eccentric, equal to 1 divided by S sub E times K sub G, and K sub G represents the thermal conductivity of the grout material as shown in equation number 5. Then we will have the general form, which is represented by equation number 6, as has been derived from the mathematical solution for the series for the circuit of these resistances as shown previously as well, but you may find the full analysis in the present reference, which would be listed in the bottom of this video. Then we have R sub F equivalent equal R offset divided by sigma, and sigma represents the obstruction factor as has been um, derived previously. Of course, this analysis of the W tube depends on two ideas. The first one is to derive an equivalent diameter, and the second one is to represent uh, the derived or equivalent geometry by using the thermal resistance circuits to find the value of R sub B. The total resistance. We have found that for the geometry, original one, which has been transformed into another geometry equivalent one, that we have the green side represents the inlet and the blue represents the outlet. And this in this analysis, we have assumed that we have a direct heat contact heat exchanger dx, then and we will analyze the model for a case where we have a condenser heat exchanger, geothermal heat exchanger. Then the fluid inlet is a vapor condensed and leaves as a refrigerant condensate. This is the dx condenser, and R sub B is equal to summation of two resistances. The first one represents the filling or the grout resistance, and the second is the pipe resistance. The pipe resistance, as we explained that before, it composes of two parts. The first one is the convection part, which is related to the condensation of refrigerant inside the tube, and the second part is the conduction through the tube wall. And the total resistance usually should include the ground thermal resistance, and if we substitute the values of R sub F and R sub P plus the value of ground resistance, then we will get equation 11. And previously we have described that under steady state conditions, which can be achieved after 1 year of operation for the heat exchanger, as it has been approved by other investigators, then the R ground equal 0.053 meter Kelvin per watt, where the thermal conductivity of soil equal to 2.42 watt per meter Kelvin. We have the heat loading, which is equal to delta T mean divided by R total, and the units will be watt per meter, and delta T mean represents the temperature difference, mean temperature difference between the condensate or the refrigerant inside the tube and the soil. And from this equation we can get the H4, which here it's meant to be the depth of the tube itself, equal Q condensation divided by small q heat loading, and the Q condensation can be calculated from a direct multiplication of mass flow rate of, for example, Freon R410A times the latent heat of the refrigerant. And from this arrangement, we may get the final results of the design for the W tube heat exchanger. Dear friends and colleagues, by now we have arrived to the case of where we have finalized our seminar for this episode. Then the closure of the present video and its content we have passed through the geothermal heat pump components, and we describe the direct contact geothermal heat pump, where we have a, heat exchanger that is composed of double U-tube that is installed vertical in the heat exchanger, and we have presented one of um, my correlations which has been published in the literature, and we have some references you may find in the description box as a list, and the content includes the first reference. It will be the first which describes the present episode, so please go through that reference to see the detailed description and analysis of the present correlation. Please, if you find that the content of the present video are useful to you and others, please subscribe and share it with your friends, and let us make the more advantages of this work, which is related to free instructive videos. And thank you for listening, and I will see you in the next part where we can use practical design for the present correlation. Bye bye.